All right, this is an introduction to puzzles in plane geometry. And this right here is the book of puzzles that we're going to use. Spoiler alert. I will be doing most of these puzzles in these pages here. So be sure to pause the video frequently so that you can work the puzzles yourself and see if you can come up with the solution. So, but now before we get to these puzzles, we have to talk about how to get this done. Okay, so we'll set that book over there. Move this stuff out of the way. So, puzzles in plane geometry, or games in Euclidean space. To win these games on this axiomatic system, to win these games, you write theorems. And a theorem is a statement proven true within Euclidean space. And Euclidean is an adjective that comes from this person's name, Euclid. And Euclid was a gamer who lived a long time ago. So the format of these challenges, or most of them anyway, go like this. They give you something, say a given, what is given, and then you're to prove something or show something, or maybe find an angle, or find a measurement, or find a property. And given is basically a string of symbols. It's a statement. And oftentimes, instead of using an alphabet, they'll use figures. They'll draw, or there'll be a sketch of some geometric shapes or parallel lines or something like that. But it's basically, that's the given part. So you have a string of symbols or some statements, and you're to find or discover or determine. But basically, it's the general format behind it all is given something, prove this other thing. And that's pretty much where we're going to leave each puzzle. We'll leave it at that. To formally kind of make it a theorem, you would just write it in a kind of a different format. You would say, let this thing here, then this condition here, or this situation here. Let this circumstance exist, then this situation will happen. This is basically the format. Or you could say, it's better to have if, basically the same thing. Suppose is another word you could use. That's basically like you're given. If you have two parallel lines and a transversal, then blah, blah, blah. So what we'll see oftentimes in the given is a combination of some words, like A is parallel to B, combined with symbols. So you got to write theorems to win. We're basically talking about strings of symbols. We're using concepts, ideas, what we can imagine in the mind to connect to the world. And we're doing that with words. An example is the definition of a circle. A circle is a set of points equidistant from a given point. So we have a definition of a circle here, but then circle is a word, and the definition is made up of words. So what are the meanings, the definitions of equidistant? or points, given point. This is the definition of the word circle. What is the definition of the word set? So we got to have a conversation about that, because writing theorems, we're talking about the truthiness of polygons and how a theorem is a statement proven true within Euclidean space. Mathematics is the art of giving the same name to different things. So as we start talking about words, let's get to some of the more basics, like equals. What this English translation of equals is the same thing. We don't really use this word in puzzles, in plain geometry. It doesn't really fit. So we use congruent, and you'll see symbols like this for congruent, or with equals, you might see this as like approximately. So congruent is preferred. And also congruent allows for reflections. You know, we use congruent because these might be like the same exact triangles, but they are two different objects, you know, in different places. So are they the same exact thing? No, not really. They're not really the same exact thing, but they are congruent. And congruency allows for flexion. So even if you slid it to a different position or rotated it, not quite the same shape. It's not facing the same way. So there's even more differences in things, yet we could say they're congruent. Similar is when shapes or when polygons have the same shape, but they could be different size. Congruency, same shape, same size, or same angle measurement, same length of line segment. Generally, we stay away from that, and we use this a lot. This involves some basic ideas and concepts like, you know, what is sameness and symmetry? How do things reflect? The prompt for a definition of distance, and then equidistance. Just to say there's an equal distance between these 2 points, we have to talk about both of those things. So that's a big part of, and that's semantics. You know, the meaning of words, that's a big part of these puzzles. But let's get back to the heart of the matter. We're talking about writing theorems. Okay, and these are words for theorems. Now, what we do in these little puzzles in this book, you might call them results, or that might be a more accurate term, but it's basically another word for theorems. Propositions as well. These are theorems. It's a statement proven true. You know, we may change, we could change the format, or just not go all the way to write it in the format of a theorem, but it's a statement proven true. So they're all theorems. If your theorem's not really useful, and because we use theorems and axioms to prove theorems, we use both those things. And once you have a theorem proven, you can use it to prove other theorems along with the axioms that you use. So all of these are theorems. If it's just something for what we have in here, it might be such a specific situation. It's not very useful in proving other things outside of that one puzzle or that one figure. So maybe it would just be called a result, but a result is a theorem. So our propositions. If you're writing a theorem that is very useful to other mathematicians, says something really big about the space that you're in, and you prove something, you have a proven statement that's like a big step kind of on the way, or a necessary step, that theorem is called a lemma. So a lemma comes before the main theorem. And then any theorems that kind of fall into your lap as a direct result of this, like logically, they're just easy to prove. Those theorems are sometimes called corollaries. A theorem that is a direct result of a big theorem. It's corollary, but they're all theorems. We're writing theorems. These are statements proven true. Axioms are statements that are not proven true. They're just accepted as true. And generally, mathematicians, we don't want to use a lot of these in our system. In our axiomatic system, we want a small number of that. The puzzles happen in the proving things. And so we like puzzles. We want to prove most things. Everything is a challenge. Can we prove one of these axioms, or do we have to have it as something that's just accepted without proof? So there's a small number of these, lots and lots of these. And the more theorems you have, the more statements you can use, because you use other theorems along with axioms to prove another statement, the next statement, or a statement about this situation that you're imagining or pondering. Word on these numbers here, like 180 or 90, as in 90 degrees. Thank the Babylonians for that. It's a Babylonian thing, and it was just their preference. There's nothing special about those numbers. It's just tradition, basically tradition. Babylonians, they liked 60. That was their favorite thing. So all their big chunks of numbers, or their counting, was done with 60 being their kind of lucky number. So that's the reason for 180 and 360, 45 degrees. Nothing special about those. Radians are a way to use real numbers instead of, a system like the Babylonians used to measure circles or angles. And ultimately, we got to get to talking about truth. Trigons are shaped with three sides. Three sides to trigon. And there's basically just three situations you can have with those sides. Either all sides are different size, a different length, or all sides are the same length. They're the same measurement. Or two sides are the same size. You might call that an isosceles trigon. If we're talking about the angles of trigons, then we say a trigon is either a right trigon. It's either right or it's not. If it's not, we say it's oblique. It's a right trigon or it's not a right trigon. And if it's not a right trigon, it's oblique. And if it's oblique, there's only two cases there. It either has one angle bigger than 90, in which case we say it's obtuse, or all angles are less than 90. And then we call that acute. So just ways to talk about trigons, because they're everywhere, thanks to circles. So a right trigon is a trigon that has an angle that's exactly 90 degrees. And remember, we're using this number only because, Babylonians. So, to the classic style rules of the game, we kind of have high-level rules to the game, or these definitions we should follow, or we can create. Maybe that's why they're high level, because you have the power to define something. And there's things previously defined, like a circle is a set of all points equidistant from a given point. A parabola is a set of all points equidistant from a line and a point, not on the line. So these are like high-level rules. Theorems are rules in a way, because if you have a theorem, you have a statement that's been proven true. You can't make that false if it's been proven true within Euclidean space. And axioms are statements that are accepted as true, and that's like the building block of theorems. But axioms, in a way, axioms are built on primitive notions, like a notion being an idea. And these are like the foundation level rules. And we won't think about these very much. We'll just use them. So when we write a lot of these puzzles, we'll be moving fast, and we won't justify. We will not cite a lot of our statements. We'll just figure that we're familiar with the theorems that came before and the axioms that we're using. So this is the construction, the classic style rules of the game for plane geometry. All right, so let's talk a bit about primitive notions. Primitive notions are things like set, point. Like, let's not have a definition for this. There'd be no end to it. We would just have to keep defining the words and the definition. Can we just agree? Everyone in their mind has the same idea of what a point is. And the same goes for a word like line. These are primitive notions, the basics of the most basic ideas. Same with plane. That's a primitive notion. We aren't going to have a definition for that. We'll just agree to agree. And under primitive notions, those things are like objects, you might say. Those notions, objects. There's also notions like relations, like an idea of betweenness. So to say that there's something between two other points. To say the point B is between A and C. That's a primitive notion. We might call a relation. And while we have definitions for circle and for trigons, tetragons, polygon, there's definitions for polygon, but there is nothing that's agreed upon. There is no consensus on polygons as a definition. But let's just make believe. Let's just pretend there's two. If we're talking about two sides in this polygon, it's a digon. Three sides, trigon, tetragon, pentagon, hexagon for 6 sides. We need 1 dimension for digon and 2 dimensions for trigon, tetragon, pentagon, hexagon, R2. You need 3-dimensional Euclidean space if you want to talk about polyhedra. The polygon, not exactly defined. Linear pair. So there'll be words like this in the games. A linear pair, you might have these angles here, because they pair together to make this line. Linear pair. This angle, and then this angle. Vertical angles. You have vertical angles whenever you see two lines intersect. Those angles are vertical to each other. And the same goes for these two angles are vertical angles with each other. Adjacent angles are angles that, say if we're talking about this angle here, this angle is adjacent, as is this angle adjacent to this. A full angle, well, full angle is 360 all the way around. Straight angle is just that, straight line, 180 degree angle. And we have exterior angles. We're talking about trigons. There might be a triangle like this. This would be called an exterior angle. Here are the axioms. Or this is not this axiomatic system. They don't actually give one in this book. It's not explicit. It's just kind of implied. There's a textbook, of course, a course book that goes with this, what I would call a workbook. And so here's something that these puzzle books work with, an example. So these rules of the game for this axiomatic system, these are axioms. So it's a recipe inspired by these gamers. So an axiom is a statement that we accept as true. We accept it as true. Like, without proof. Like if you have 2 points, this point, any 2 points, let's call one A and call one the other point B. How many lines go through both those points? 1. Not going to prove that because it's obvious. Everyone gives that same answer. It's intuitive. That's intuition. And it's so very basic. It's just a simple idea. Let's just make that an axiom. Intersecting lines. And how many points do they intersect? How many do they have in common? How many points? 1. Prove it? Nope. Not going to try. We won't waste our time. There's no point. It's obvious. Let's just accept that and move on. It's an axiom. It's a statement accepted as true without proof. We're playing these puzzles, doing this game in an axiomatic system. Transitivity of congruence. So that's basically saying, well, if X is congruent to Y and Y is congruent to Z, then X is congruent to Z. Transitivity of congruence. Okay, that's an axiom. That's just a truth about the universe, or at least the universe according to this particular system, this axiomatic system. That's a statement we're just going to accept as true. Doesn't have to be proven. Another important axiom is a statement that says planes exist, or a plane exists, there exists 3 non-collinear points. We're basically saying R2, real number plane, Cartesian plane is a thing. A plane exists. There exists 3 non-collinear points. So in math, it'd be written like this. There exists X. There exists Y. There exists Z, such that it is not the case that Y is between X and Z, and not the case that Z is between Y and X, and not the case that X is between Z and Y. This is an axiom. Planes exist. We're just going to accept that as true. No reason to prove that. We have Archimedes' axiom. We'll talk about that later, but that basically says you can always make something bigger. Archimedes' axiom, if you have that length of something, however long that line is, and then maybe you have a smaller one, no matter how small this is, and no matter how big this line is, when compared to each other, you can always get a number, big enough number k, so that a k number of these little things, these dashes, however small they might be, a k number of them will always be longer than this big thing. It's Archimedes' axiom. And then we have Euclid's 5th axiom. And that's what makes this a Euclidean space. It's what makes this Euclidean geometry, is Euclid's 5th. Obviously true? We'll see. Now, why Euclidean geometry? Why are we calling it Euclidean geometry? It was just geometry for 1,000 years. It was just the world. It was just what was thought to be true. All the angles, you measure all the angles of a trigon, it adds up to 180. That's just geometry. It's the only way to do geometry, to think about these ideas, these concepts, these shapes. It was the universe. It was just geometry. And if one looks at mathematics as the language of science, then we'll go back to Galileo. Now, Galileo, he did not invent the telescope. He heard about the invention of the telescope. He got news about the first telescope existing. And he thought, that's a pretty good idea. I'll build one even better. So he's the guy who made the second telescope in the world. And he saw the moons of Jupiter. So he didn't invent the telescope, yet he proved that there is no such thing as ascending or descending in the world, in the universe, that there is a universe, that there's not a domed ceiling. There is no up. There is no down. Galileo was the first of civilized culture to know this, to discover this. And he could make statements about the world like this. The space, the distance that something travels in free fall is proportional to the time that it has spent falling squared. Galileo looked at these numbers. He could look at these numbers here. 1 plus 3 plus 5 plus 7 plus 9 plus 11. See how many numbers we got there. 1, 2, 3, 4, 5, 6. The first 6 odd numbers. So I'll square 6, and that gives me 36, and that's what these add up to. Verifiable statements about the world. He took these numbers and connected them to gravity. And then he was able to prove mathematical theorems that related to what was observed and measured in the real world. He could make predictions. He could hypothesize, set up a situation, and say what was going to happen next. And anybody could duplicate that around the world. A verifiable statement. Now, of course, there were organizations at the time who had been saying unverifiable things for ages. Their statements are not in any way verifiable. And so he kind of got in trouble with authority. But maybe this was a really big point in history where truth and prediction, I think, were coming to be expected of mathematical symbols, theorems, theories in science, connecting with theorems in mathematics. The year Galileo dies, Isaac Newton is born. And that guy, he came up with some ways to talk about the universe. One of them being this. The force between two objects is the same thing as the gravitational constant of the universe, G, multiplied by this ratio. The mass of the two objects over the distance between them squared. Isaac Newton invented calculus to explain the orbits of the planets. Truth? One might think so. However, there is one thing that Isaac Newton's mathematics and physics, laws of motion, laws of gravity, couldn't explain. While planets moved around like this, agreeing with Newtonian physics, not Mercury. There was one planet, the one closest to the sun, that goes around the sun like this. Of course, it doesn't intersect the orbital paths of these other planets. I'm just drawing this big so you can see Mercury goes around the sun like that. And a guy named Einstein figured that out. So this is the way things curve space-time, and this is the path, how things need to follow that curvature. Proven? Verified, most definitely. The general theory of relativity, GTR, again and again and again, it is well confirmed. Maybe even more so than theory of natural selection and evolution. Well confirmed. Proven? Like a proven statement in plane geometry? When you're doing puzzles, that kind of proof? Proven that way? It's clearly using a lot of math. Proven? Albert Einstein said, "No amount of experimentation can ever prove me right. A single experiment can prove me wrong." Now he knew no matter how many times it seemed like he had it spot on, that was exactly it, his map might not actually match every part of the territory. Heisenberg's uncertainty principle in quantum physics says the more you know about where something is, the less you know about where it's going. The less you know about the location of something, the more you can know about where it's going. In other words, you can't observe something without changing it. Heisenberg said, "Every tool carries with it the spirit by which it has been created." We have to remember that what we observe is not nature herself, but nature exposed to our method of questioning. As far as the laws of mathematics refer to reality, they are not certain. And as far as they are certain, they do not refer to reality. Albert Einstein said that. If you want to go back to mathematics, away from the physicists and their doubts, and work within an axiomatic system, a formal system, where there's rules for how you string symbols together, well, then we get Gödel's incompleteness theorem. So even if we're in a system that tells us how to derive theorems, we run into problems. There's an incompleteness to the system. And a corollary of this theorem, and remember, corollary is just another word for a theorem, but it's a theorem which falls right out of another theorem. A straightforward path to proof. Corollary of the incompleteness theorem is the definition for truth does not exist. So we have general theory relativity in real life. Meaningful maps are basically all that physics, science, mathematics can make with regards to the world. And the map is not the territory. And it's an amazing philosophy that can be so flexible, create so many maps, accurate to one scale or another. This quote You have to look up who said this as homework. Report back. Who said this quote? Whoever undertakes to set himself up as a judge of truth and knowledge is shipwrecked by the laughter of the gods. So now to puzzles and plane geometry. To win these games, we're going to write theorems. A theorem is a statement proven true within Euclidean space.